This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 2301 statics. This is a composite of a problem that we had on a recent test. And I've kind of changed the numbers a little bit. So it's not exactly like any one version on the test, but it's very close. Only the angles have been changed and the weight over here has been changed. You should be able to use this solution to go over your solution on your version of the test and make sure you can work it out. I'm given a weight on wheels on a sloping surface that slopes at a 512, which means 512.13 slope, attached to a cable AB, which is knotted at B, with the cable BC supported above at point C. Then also at the knot I have this cable that runs at a 1-to-1 slope, which means that length is square root of 2, the hypotenuse. Runs under this pulley, over these two pulleys, and back down, and has a 250-pound load supported from it. I'm told that the system is in equilibrium, so it's just balanced. Everything's balanced. First thing I wanted to know was a free body diagram of knot B. It's pretty simple. I just take knot B, remove it from its supports, remove it from its environment, and just replace those cables that are attached to it with vectors. TAB on this side, going at that slope of the sloping surface here, 512.13. I have TCB going up vertically to that point C, and then I have the force in the cable TBD, which is the cable that runs over the pulleys and to the weight. Remember, it's going at a 1-to-1 slope. So I've shown that. So I can go real quickly. The key to solving these problems is doing a good free body diagram and then doing sum of forces. So I can go over and just do a simple free body diagram of the weight itself, the 250-pound weight, and I can see obviously the force in the cable, which at this point is FG, TFG, has got to be equal to the 250-pound weight. So that force is 250 pounds, and I can then substitute that into this free body diagram, which we'll use here in a minute. Second part of the problem was number 14. We want the tension in the cable BDEFG. Well, here we're going to use the rule of pulleys, which is that pulleys do not change the force in a cable. They just merely redirect the force. So if it's 250 pounds in that cable FG right there, I got that from the free body diagram, it's 250 pounds here, it's 250 pounds here, it's 250 pounds here. So that's why I can substitute that in for the force in TBD, as I've called the vector hooked up, connected at knot B, and therefore the force in that cable is just that 250 pounds. Very easy. I'm sure you feel guilty right now if you missed that one. Number 15 was find the tension in cable AB, the part that's attached to the weight on wheels. Okay, here I've redrawn the free body diagram, and I've broken the forces in TAB and TBD into their X and Y components. Kind of helps me visualize what I'm dealing with. And so I can see here that if I can just work with the X direction, TABX and TBDX, I can solve for the force in TAB directly, because I know that TBD is 250 pounds. So I write a sum of forces equation equal to 0, positive to the right. It's negative TABX plus TBDX. Substitute what I know about it. This is the 12/13ths of TAB is the X component. It's negative to the left, plus 1 over the square root of 2 times this known force in the cable TBD of 250 pounds. Do the math, switch 1 to the other side of the equal sign, and I get that TAB is this function, this value, Just inverted that 12/13 and made it 13/12. 250 over square root of 2 works out to be 192 pounds. Okay, just as a sideline, we weren't asked this on the test, but I could call it 15A. What's the tension in cable CB? Well, once again, it's just a simple sum of forces, this time in the Y direction. Positive is up, it's equal to 0, minus TABY, it's down, minus TBDY, it's down, plus TCB. I know all the values, so that's negative 5/13 of the total tension in cable TAB, which is 192 pounds. Negative 5/13, 192, minus 1 over the square root of 2 times 250, which is just from this relationship here, plus TCB. TCB works out to be 250 pounds. Isn't that interesting? Okay, now back to the test and what I was asked on problem 16, the weight of the cart at A. I think a lot of people panicked on this question, and all you need to do is, when in doubt, draw a free body diagram. So here's the free body diagram of the weight. I've taken the wheels out, and I've just substituted this normal force here that I was told is exerted perpendicular to the slope. So I've drawn a little perpendicular sign. You can't see it there, it's kind of obliterated there, covered up. But it's perpendicular to the slope of the weight's resting on. So up here I did a little geometry to prove to you that if my slope is 5 to 12, that really is just a way of describing that angle. So to the horizontal. And if that angle is theta to the horizontal, then another parallel line to the horizontal is drawn up here. So that's theta, so that's theta. And then if I draw my normal force, which is perpendicular to the slope, I can see that it's going to make an angle. If that's theta, and this is perpendicular to this one, then this one's perpendicular to this one. So if this is theta, this is 90 minus theta, the angle between that green horizontal line and my normal force line, perpendicular to the slope. If that's 90 minus theta, and that angle is 90 degrees, the green grid, that angle's got to be theta. And if that angle theta is theta to the vertical, which is the same angle as this line to the horizontal, then the slope relationship of the normal force has got to be 5 to 12 in that orientation. So I use that down here. I've got my normal force at that 12:5 ratio or slope. I've got my weight, which is straight down. That's what I'm trying to solve for. And I've got the force in the cable AB, which I've just reversed from this one right here, this free body diagram. And those are its components, 5 over 12. I've drawn in my components, X and Y. And I can see that if I solve for the sum of forces in the X direction, the weight has no force in that direction, so I just get negative NX because it's to the left, and I've assumed positive to the right, plus TABX, which is positive because it's to the right. I do the components. The X portion of N is 5/13 and it's negative because it's to the left, plus the X component of TAB, which is 12/13 times 192. Doing the math, I get NX is equal to 13/5 times 12/13 times 192, or 460 pounds. Almost there. I do a sum of forces in the Y direction. It's equal to 0. I have negative W plus the Y component of N, which is 12/13, plus the Y component of TAB, which is 5/13. And do the math, I get negative W is equal to this plus this, so it's 498 pounds.